Hey, grade 10s. So in this lesson, I'm going to go over multiplying and dividing rational functions. So this is the second lesson that we covered on Thursday. So I'm just going to briefly go over this topic again. So I know some of you went through the PowerPoint, but you were still a little bit lost. So I'm hoping this helps. So pretty easy learning objectives is just to learn how to multiply and divide rational functions, and specifically also how to state the restrictions when you multiply and divide rational functions. So how do you multiply rational functions? So before we even get to that, let's just go back to basics. How do you multiply fractions, right? Because really what we are going to notice is that multiplying rational functions has a lot to do. It's very similar concept to multiplying rational functions. So they're very similar. Multiplying rational functions with multiplying fractions. So what we're really doing here in this case is simply if we have two fractions and we're multiplying them, I know I can easily multiply it by multiplying the numerators together and multiplying the denominators together. And then this ends up giving me something of the form a times c if those are my numerators, and this is divided by b times d, which are my denominators. So if you want to multiply rational functions of the form a over b and c over d, and it's probably better if we actually write it as ax over bx, because technically it's a function. And then we have cx over dx. We know that we can simplify this into something quite easy. We simply just multiply the a function times the c function, and we multiply the b function times the d function. That's really what we're doing. It's quite simple, actually. So in terms of restrictions, your restrictions are a similar idea as before. The only difference is that we had to specify that the denominator b here of the first fraction of the first rational function and the denominator here of the second rational function cannot equal 0. And again, why can it not equal 0? Because we know that we cannot divide by 0. So you're essentially just checking to see when each of the denominators is equal to 0. But you do this before you cancel it out. Okay, so we're still going to be canceling out our common factors just like we did before. So if you have a common factor in the numerator like x plus 2 over 4 times x plus 2, this is a very simple example. I'm allowed to do this. I'm allowed to cross cancel it out like that. But before you cross cancel or simplify it, you need to first identify what your restrictions are. So you do that before canceling out. Okay, so you check when the denominator is equal to 0. And that's what we're doing here. So here's an example. So multiply and simplify, and then state the restrictions. So once again, what makes this question hard is the fact that there is a lot of different expressions going on here, right? But before I even multiply and try to simplify, we need to factor, right? That's the very first thing. We need to factor this out. This one is already factored out, so we don't have to do anything. This is almost factored-ish, right? But we have a little bit more to do. This needs to be factored, and this also needs to be factored. Luckily, I hope some of you actually realize that there are relatively easy ways to factor this. So the first numerator there, x squared minus 4, we notice that this is a difference of squares. So a difference of squares you can easily factor like so. So I'll show you how to do this. We take x plus 2 times x minus 2, just like that. And we can go to the next one, x squared plus 9x plus 18. This is the sum and this is the product. So what adds up to 9 multiplies to give you 18. So that would be 6 and 3. And you can double check with me. 6 and 3 will add up to give me 9, but multiply to give me 18. And then the last one, 4 minus 2x. We know that I can common factor out the 2. And this leaves me with 2 minus x, just like that. So then that means that my, my expressions can simplify to x plus 2 times x minus 2 over x plus 6 squared. And in the numerator over here, I have x plus 3 times x plus 6. And it's divided by 2 times 2 minus x. So what do I notice next here? Well, I hope that I can cancel things out. I hope I can cancel factors out. And it doesn't seem like I can factor a lot out yet, but there is more simplification than you think. So first thing, I noticed that x plus 6 is common here and in the numerator and the denominator. Now, I don't cancel it out completely. All I do is simply cancel out one of the x plus 6 factors there. And I'm actually left with x plus 6 in the denominator right here. So I notice that x plus 6 comes up here, and x plus 6 also comes up here, but it's x plus 6 squared. So when I divide x plus 6 by x plus 6, I end up getting 1, but I still have a factor of x plus 6 in the denominator here. So just keep in mind that I reduced that exponent 2 to exponent 1, but it's still, that factor is still there. If any of you learned about negative exponents, you can also apply the exponent laws as well, but I feel like most of you have not done that, so you can maybe probably avoid that for now. What else can we cancel out? Well, I also noticed that the x minus 2 is kind of similar, but not quite, kind of similar to the other factor in the denominator, which is 2 minus x. So they're quite similar to each other. So it makes me think maybe I can't cancel them out. But this is where people kind of run into an issue. X minus 2 looks very similar to 2 minus x. The only difference is the order in which they're subtracted. Luckily, because of the order in which because the only difference is the order in which you subtract, we actually notice that that's a special property with, and if you want to understand that, think about real numbers. We know in real numbers that 3 minus 5 is -2, but we know that 5 minus 3 is 2. So notice that the only difference between the two answers is that one's positive, one's negative. So it's the same idea here. X minus 2 and 2 minus x are actually equivalent, almost equivalent expressions. They're not the same, but they're almost equivalent. The only difference is that one is simply a negative. It's a negative expression of the other. So if I want to rewrite 2 minus x as x minus 2, I can just simply put a negative sign in front. Or if I want to write x minus 2 as 2 minus x, I can simply put a negative sign in front as well. So this is a little trick that we can use here. So that basically means that the x minus 2, let me erase this so there's more space here. I noticed that the x plus 6 cancels out here. Like I said, it cancels out there, so you're still left with x plus 6. And then I noticed that the x minus 2 and the, x minus 2 and 2 minus x are similar, but again, once the one big difference, we just switched the order. So because of that, I had to make sure that I switch the sign, and that's where that -1 is coming from. I know some of you were wondering about that. So what I noticed is that this cancels out, and then I still end up with a -1 right there. So keep in mind and really remember this, because this will come up a couple of times. If it has something like x minus 5 and divided by 5 minus x, very similar expressions. What's the only difference here is that one is sorry, you would think that you would end up getting 1, but it's actually not 1 that you end up, this simplifies to. You actually end up getting -1. And the reason for that is because they have the same absolute value. Think of it that way, right? But if we're looking at the distance between them, but they are not the same sign, right? And again, always think about real numbers if you're ever confused about any algebraic principles, right? Think about what you would do with real numbers. It's a similar concept when we look at algebra, right? So what we notice here is that x minus 2 and 2 minus x will cancel out, and I still have to multiply by -1 there. So now we end up with x plus 2 times x plus 3 divided by, divided by x plus 6. So we still have that factor x plus 6 times -1 times 2. And this will simplify to -1 times 2, which is obviously -2, and I put the -2 in front. And then I end up getting -2 times x plus 6 in the denominator, and in the numerator have x plus 2 times x plus 3, just like that. And that is as far as I can simplify it. I always check, can I go any further? No, I cannot. And if you can't go any further, that's fine. Just leave it as it is. And on your tests, I will tell you right now, I will not give you a question where you can't simplify anything, right? So you will know if you're doing this right or wrong, if you can have common factors that you can cancel out. If you can't cancel them out, then you're probably doing it wrong, right? At least on my test, because you would be able to do more. The last step here is just this is just more notation, standard convention here, is that we normally like to put the negative in the numerator or in front of the whole fraction. In this case, I'll put it in the numerator like that. We normally don't like the negative sign in the denominator. And then the restrictions. So we hadn't discussed this, but I'm hoping that the restrictions make sense now. What you're doing is you're simply checking when the denominator is equal to 0. So in this case, you check when is x plus 6 equal to 0, So you check x plus 6 is equal to 0 when x is equal to -6. And over here, we can do a little bit of math. 4 minus 2x, when is that equal to 0? That's equal to 0 if I bring the 2x over. You get 4 is equal to 2x, and then you divide by 2, x is equal to 2, okay? So that's my other point when the denominator is equal to 0. So then I simply state this as x cannot equal -6 and x cannot equal 2, because those are the 2 points at which the denominator would equal 0, which you know is not allowed. So how do you divide rational functions? So to divide rational functions, it's actually not too bad. All you're really doing is simply is switching your division question into a multiplication question. So remember that when we divide by a fraction, you simply multiply by the divisor or the second rational, the second function, the second fraction. But in this case, because we're talking about rational functions, we're simply finding the reciprocal of the divisor. So that means that instead of dividing by c over d, if that's your rational function, we're going to multiply by d over c. So we have to multiply by the reciprocal. So we have to switch this second rational function there. And then once you do that, you multiply the numerators and denominators together, and then this simplifies to a over b times d over c. And then we end up getting an easier expression to work with, because we know how to, and again, we know how to multiply rational functions. That's the easy thing, right? So really all you have to do is flip the second rational function. You exchange the numerator and denominator, and then you simply multiply. So this is just like how you would divide fractions, right? So if you recall fractions, dividing by fractions, if I give you something like this, 3 over 4 divided by 5 over 8, I simply rewrite this as 3 over 4 times 8 over 5. So it's the same idea. I simply multiply and then I reduce it. So that's what we're going to do here. Now, the restrictions, this is where it gets a little tricky. And I would honestly, just for the timing's sake, I would just focus on just remembering this. For your restrictions, and I hope this still makes sense, you would actually be checking 3 different spots. You're going to be checking when the denominator is equal to 0. So I'm gonna erase this one so I have more space here. You're going to be checking when the denominator is equal to 0. You're going to be checking for the denominator, the second rational function. But on top of that, you're also checking the numerator of the second rational function you're dividing by. Why do we check the numerator as well? The reason you're checking the numerator in this case of the rational function you're dividing by, the reason you have to do that is because this numerator here actually will become the denominator when we decide to change it from division to multiplication, right? So because of that, the numerator in the second rational function will then become a denominator. And so we still have to check when is that denominator equal to 0, because again, we run into the same issue. You can't divide by 0, right? And again, same idea as before, you check the restrictions before you cancel out, okay? So let's look at an example here. So if I give you p squared minus 1 over 6p squared plus 6p plus 1 divided by p plus 1 over 3p plus 1. It's kind of hard to say. So what we're going to do first, once again, we notice that we cannot just easily start canceling out. One thing I want to warn you about, and just be careful with this, a lot of people think that you can just cancel out the p or cancel out the 1 or cancel out the p squared. No, okay? Big N-O, no. Do not do that, okay? I cannot warn you enough about that. You're not allowed to do that because this is not written, this is not factored out as products, right? Once we write this as a product of different terms, a product of different polynomials, then we can start cross-canceling out. But for now, we can't do that. So first we have to factor each of the expressions. So we factor out p squared minus 1. We write that as p plus 1 times p minus 1. And then we rewrite 9p squared plus 6p plus 1 as 3p plus 1 times 3p plus 1. And how did I do that, by the way? So I'm showing less steps here because I'm going to assume that most of you know how to do this now. You notice it's a trinomial, right? Everyone can hopefully see that. It is, so we can't use difference of squares, you can't common factor. But we might notice that the first term here and the last term there are perfect squares. And you can quickly double check that, the square root of 9p squared is 3p, the square root of 1 is 1, and just quickly double check. Is 6 2 times the square roots. Yes, it definitely is. So you can use the perfect square trinomial factoring to help you solve this. So you get 3p plus 1 times 3p plus 1. You could also use sum and product as well, right? And so you've just tried to think of two numbers that add up to 6 but multiply to give you 9. So if you think of the two numbers would be 3 and 3. So then you write 3 over 9 and 3 over 9. And this is the Aussie method, right? You reduce it to lowest terms. Oops, I forgot to do that. You reduce it to lowest terms. That's 1 over 3 and 1 over 3. And then you rewrite it as 3p plus 1 and 3p plus 1, which is basically what we got here. So we rewrite 3p plus 1 obviously as 3p plus 1 times 3p plus 1, or we could do 3p plus 1 squared. But what you notice here, and the reason I kind of like to leave it like this, is because I'm hoping that something will cancel out. And it does, because when I divide by my rational function here, I know that I can simply flip the fraction. So when instead of writing this as being divided by p plus 1 over 3p plus 1, I can rewrite it as multiplied by 3p plus 1 over p plus 1. And then I realize here that I can actually cancel this out. And that reduces, and p plus 1 and p plus 1 also cancel out. And then I'm left with something really, really easy. I'm left with p minus 1 as the only factor in the numerator, and 3p plus 1 as the only factor in the denominator. And then that's it. I'm done. Now my restrictions. Now notice that with my restrictions, I didn't just check the denominator when I simplified. I have to go back to the original question here. I have to check when the denominator here is equal to 0, which is, and we know, we can tell here that 3p plus 1 squared is going to be equal to 0. There's only one point which is equal to 0 when p is equal to negative 1 over 3. And how did I get that? I'll just show the work here because I know some of you might be a little bit lost. That's okay. So I bring the 1 over, I get negative 1 is equal to 3p, and then of course I divide by 3. And that's how I got negative 1 over 3. So that is one of the restrictions. 3p plus 1, notice that that's the exact same. We're going to have the exact same restrictions as this, so I don't even have to check. And really important, I have to check the restriction here. So I have to check when is this equal to 0? What is the 0 of this function here? This numerator, which becomes the denominator. So I can clearly see here that this is, the 0 is negative 1, which means that the restrictions are p cannot equal negative 1 over 3, and p cannot equal negative 1, and that's it. So I hope that kind of makes sense. And that was basically it for multiplying and dividing rational functions. So that was actually a little bit easier, especially if you understood the last lesson. So if you want to multiply rational functions, you simply multiply the numerators and denominators. Pretty simple. And you cancel out any common factors. Then you state the restrictions by looking at the functions before you cancel out. And then to divide rational functions, you basically follow the same steps. The only difference is that you're simply multiplying by the reciprocal of the second rational function, or the divisor, and then you follow the same steps. So essentially you're changing your division question into a multiplication question, but you follow the exact same steps after you switch it to a multiplication question. And keep in mind that this is just like fractions. You do not need a common denominator to multiply or divide. When we get to adding and subtracting, you do. And we'll talk a little bit more about that. And that is basically it.